Hey everyone, welcome back. I am absolutely thrilled to have you here for another explainer. Today, we're going on a truly fascinating journey. We're literally going to shrink ourselves down, starting from the microscopic and going all the way down to the absolute quantum level. We're talking about the incredible, mind-blowing engineering that happens entirely out of sight, yet, it completely dictates our modern world.
It really begs the question, how do we actually measure the invisible? Well, today, we are going to demystify the unseen technologies that power everything around you. I'm talking about the hidden mechanisms inside your smartphone, the life-saving diagnostic medical devices in hospitals, and even the sensors that keep your car perfectly on the road. We are going to look at exactly how we measure forces, light, and even individual molecules when the scale is almost too small to even comprehend. Okay, let's dive into this. Here is our roadmap for today. We'll start with the microworld of MEMS, then we'll add light with MOEMS and leap all the way down to nano-sensors. After that, we'll hit quantum precision with SQUID sensors, before wrapping the whole thing up with the micro challenges these technologies face in our macro world. Section 1. The microworld of MEMS. Let's start with our first stop on the scale of the invisible.
First things first, we need to establish our baseline physical scale. MEMS, which stands for Micro-Electromechanical Systems, are basically engineering systems designed to achieve specific electromechanical or electrochemical functions. And what's really amazing here is the size. The components inside a MEMS device are typically sized somewhere between 1 micrometer and 1 millimeter. To put that into perspective for a second, a single human hair is about 100 micrometers thick. So within this incredibly tiny footprint, a true microsystem usually packs in 3 major components: microsensors, actuators, and a processing unit.
And this brilliantly illustrates the core flow of a MEMS device. It's actually pretty elegant. An input signal comes in, the core microsensing or actuating element interacts with that physical input and then passes it right along to the transduction unit. Powered by a supply, it processes that information into a readable output signal. So it's an entire integrated system of mechanics and electronics just miniaturized onto a single tiny chip. To really appreciate why MEMS is such a massive game changer, just look at the automobile crash airbag deployment system. The old tech required several bulky accelerometers made of discrete components, and they had to be mounted in the front of a car with totally separate electronics near the airbag itself, and it cost over $50 per device. But MEMS technology allowed engineers to integrate the accelerometer and the electronics onto one single tiny silicon chip for just a few dollars. They're smaller, lighter, vastly more reliable, in a mere fraction of the cost. And because they are so cheap and so reliable, these micro-inertial sensors and gyroscopes are quite literally everywhere. We just talked about car airbags, but MEMS are also the exact reason your Apple iPhone knows when you rotate the screen, and they're what allows a Nintendo Wii controller to track your hand movements in three-dimensional space. Grounding this abstract technology in reality, you probably have a dozen MEMS devices within arm's reach right now.
Section 2. Adding light with MOEMS. Let's see how this builds when we combine microfabrication with optics. Enter MOEMS, or Micro-Opto-Electromechanical Systems. This is an incredibly exciting interdisciplinary field. It takes that mechanical and electrical integration we were just talking about and introduces optical signals into the mix. Operating on that exact same micrometer scale, these devices fundamentally sense and manipulate light. They independently utilize batch processing and micromachining, very similar to how we make integrated circuits, but they incorporate special materials like silicon, silicon dioxide, and gallium arsenide specifically to direct and modulate optical signals.
The applications here are just incredibly diverse. We're talking about manufacturing giants like Intel and TSMC using them for microlithography to make smaller transistors, all the way to the digital micromirror devices humming away inside modern projectors. In our massive data centers, they act as optical switches for wavelength division multiplexing. But it goes way beyond just electronics. MEMS technology is currently powering microneedles for painless vaccines, and even the sophisticated collision avoidance systems in your car. It's truly a bridge between computation and the physical world of light.
Section 3. The power of nano-sensors. Now hold on tight, because we're going to drastically zoom in. Welcome to the world of nanosensors. We are shrinking down from the realm of micrometers into the astonishing nanoscopic level. These are devices functioning at a scale of just a few nanometers. A nanometer is 1/1000th of a meter. At this incredibly tiny scale, these sensors detect minute physical, chemical, or biological quantities. They are so incomprehensibly small that they can target individual cells right at the molecular level. And they achieve this biological precision using specific targeting ligands that act kind of like tiny magnets, attracting a specific marker of interest which we call an analyte. Logically, here is exactly how that chemical sequence plays out. Step 1, the targeted analyte diffuses from a solution and arrives right at the sensor surface. Step 2, that analyte reacts with those specific, highly targeted ligands we just mentioned. Step 3, this precise chemical reaction fundamentally changes the physical chemical properties of the sensor surface. And finally, Step 4, a transducer converts that tiny nanoscale property change into a readable electrical signal. This entire process can occur on a surface made from astonishing materials like carbon nanotubes or highly customized nanowires. Now, what's really interesting about this slide is how this nanoscale chemistry translates to actual medical miracles. By using chemoresistive nanosensors made from nanowires and nanofibers, we can detect specific volatile organic compounds in human breath. For instance, detecting acetone acts as a biomarker for diabetes, ammonia for kidney dysfunction, and incredibly, toluene for lung cancer, diagnosing severe diseases simply from the chemical composition of an exhaled breath. Absolutely mind-blowing. The literature explicitly points out the versatility here, stating that graphene and its derivatives are widely used as electrical nanosensing materials. Dopamine, a prevalent neurotransmitter, most notably Parkinson's disease, was detected using graphene oxide. So these electrical nanosensing materials provide unique, real-time insights into critical physiological parameters. And it's not just for humans either. These exact same nanosensors are used in agriculture to gather real-time readings of soil pH, moisture, and residual pesticides. It's the ultimate environmental awareness, literally at the atomic level. Section 4. Quantum Precision, SQUID Sensors. We are reaching the ultimate extreme in our journey of scale today.
If you thought nanosensors were precise, wait until we look at how we measure unthinkably weak magnetic fields. This brings us to the SQUID sensor, which stands for Superconducting Quantum Interference Device. A SQUID is a highly specialized, extremely sensitive magnetometer. It relies on superconducting loops that contain what are known as Josephson junctions. While the quantum physics behind this are complex, the main takeaway is simple. SQUID sensors are the absolute pinnacle of quantum precision and measurement. To give you an idea, they can detect magnetic fields from neurological activity in your brain, signals that are billions of times weaker than the magnetic field of the Earth itself. When you need to detect a ghost, you use a SQUID.
Section 5. Micro Challenges and Limitations. We've zoomed all the way down to the quantum level. Now, let's zoom back out.
Because while these devices are total marvels of engineering, they still have to survive in our very large, very messy world. Integrating a MEMS sensor with standard microelectronics is absolutely crucial, but as you might imagine, engineering this isn't easy. Manufacturers have to use incredibly complex monolithic approaches, especially when dealing with the extremely small electrical signals these sensors output. They might build the electronics first, put the MEMS in the middle, or build the MEMS first and carve out sacrificial layers just to protect the fragile mechanics while the electronics are built around them.
So the crucial point here is what we call the packaging problem. If you build a standard computer chip, you seal it tight in plastic to keep the environment out, right? But a MEMS device or nanosensor is designed specifically to sense the environment. A pressure sensor needs to physically feel pressure. A gas sensor needs to touch the gas. Therefore, unlike standard semiconductor packages, MEMS packages must provide mechanical support and a fluid or optical interface, all while somehow keeping moisture, dust, and corrosive contaminants out. And when that protection fails, the microworld breaks down in some pretty unique ways. We see three main failure mechanisms acting as constant adversaries for engineers here. The first is stiction. Because the parts are so impossibly small, microscopic adhesion forces cause moving surfaces to simply stick together permanently. The second is delamination, where the bonds between vastly different thin film materials just fail and peel apart. And finally, dampening. Because MEMS rely on perfectly tuned resonant frequencies, even atmospheric gases or outgassing from the packaging itself, or high-frequency ultrasonic wire bonding can alter the frequency and ruin the sensor's accuracy. It is a constant, ongoing battle against friction and the environment.
But despite these immense packaging and fabrication challenges, the relentless miniaturization of technology just keeps pushing forward. From the MEMS accelerometers in your pocket to the MOEMS optical switches in data centers, all the way down to disease-detecting nanosensors and quantum-level SQUIDs, we are truly mastering the unseen. Which leaves us with this incredible thought to ponder today. As sensors continue to shrink past the nanoscale, what invisible worlds will we be able to measure next? Thank you so much for joining me on this explainer. Keep asking questions, and I'll catch you on the next one.